Hello, fellow Homo sapiens, and welcome. Take a moment to settle in. Whether you're preparing to sleep, unwinding after a long day, or simply letting your mind wander while cooking, showering, or working with headphones on, this space is for you. Here we explore slow science and quiet storytelling, no hype, no noise, just careful history, humble archaeology, and thoughtful reflection told softly. If this kind of long-form content speaks to you, consider liking and subscribing. It helps others discover a calmer way to learn and grow curious. I'd also love to hear how you use these stories. Do you listen at night before sleep, or during the day while working? And don't worry if you drift off in the middle. I've added timestamps in the description so you can easily return and continue the journey, because every part of the story is worth hearing through. So, wherever you are, stay curious, stay calm. Tonight, we begin. Before we set off, let me ask you something. Where in the world are you listening from tonight? Is it evening where you are? Perhaps with the day's sounds fading and the sky already dark? Or maybe it's morning and you're greeting the day with this voice accompanying you like a background hum. Time zones scatter us. Yet here we are together, connected through a single thought about the universe. If you find this little voyage soothing, or if it simply helps you wind down, I'd be grateful if you gently tap the like button, maybe even subscribe so others who might need a calm pause can find it too. So, get comfortable, let your thoughts ease, and let's begin. Because somewhere out there, scattered like invisible embers in the blackness, are stars that died, and yet refuse to fade entirely. Their story is violent, their nature is extreme, and yet their existence reveals so much about the fabric of reality. Imagine for a moment the life of a massive star, not one like our sun, which is stable and calm by comparison, but one many times larger, blazing hotter and brighter. A star like this lives fast and dies young. Its lifetime is measured in millions of years, not billions. For a while, it maintains a delicate balance, its outward pressure from nuclear fusion holding back the inward pull of gravity. But gravity is relentless. It always waits. And when the star's fuel runs out, when there is no more nuclear fire to hold it open, gravity wins. The star collapses in on itself, imploding with such violence that its outer layers blast away in a supernova. The core that remains is crushed beyond comprehension, and in that collapse lies the birth of a neutron star. Now, it's one thing to say a star collapses, but let's consider what that really means. Picture something the size of our sun, a sphere nearly 1,000,000 miles across. Imagine all of that matter being squeezed down until it's only about 12 m wide. That's about the size of a city. Something you could cross in less than an hour by car. Yet, this tiny sphere still contains more mass than the sun. 1 teaspoon of it would weigh billions of tons on Earth. Matter in this form no longer resembles anything familiar. The protons and electrons that once danced freely are forced together into neutrons, packed shoulder to shoulder until there is no more room. This strange remnant is not simply a small star, it's a whole new category of object balanced on the razor's edge between existence and collapse. If the mass is a bit higher, it could fall into itself completely and become a black hole. If it's a bit lower, it may remain as a white dwarf. But in this precise extreme range, it becomes something in between. Dense enough to warp space and time, yet still visible, still radiating energy, still leaving its mark on the universe. You might wonder why they're sometimes called the deadliest. Part of the answer is simply their density. Get too close to a neutron star, and the difference in gravitational pull between your head and your feet would tear you apart in an instant. That effect is called spaghettification, though the name doesn't really convey the horror of what it means. Their magnetic fields are so powerful that they can strip electrons off atoms from thousands of miles away. Some neutron stars emit beams of radiation that sweep across space like cosmic lighthouses. If Earth were in their path, life as we know it would be in jeopardy. They are extreme in every possible way, but tonight we'll explore them gently at a safe distance with awe rather than fear. Think of them as laboratories of physics. They allow us to glimpse matter under conditions that can never be recreated on Earth. By studying them, astronomers uncover secrets about the fundamental forces of nature. And while they're deadly in theory, in practice, they're simply too far away to trouble us. Instead, they exist as reminders of the vast, strange universe we live in. Even as we talk about them, it's worth pausing for a moment. Somewhere in a distant patch of sky, a neutron star spins silently, unseen by most, unnoticed except by careful instruments. It's easy to forget that such things exist at all, given how distant and abstract they sound. Yet they are real. each one a monument to the death of a massive star, each one a marker in the history of the cosmos. Their story doesn't end with their birth. Some spin at incredible speeds, hundreds of times each second, faster than a kitchen blender. Some generate magnetic fields 1,000,000,000,000 times stronger than Earth's. Some merge together in violent collisions, creating bursts of energy so intense they outshine entire galaxies. And from those collisions, elements like gold and platinum are scattered into space, seeding future stars and planets. When you hold a piece of jewelry, you're holding the remains of a star's death throes. Neutron stars might be deadly, but they are also generous. Without them, many of the elements that make up our world would never exist. Life as we know it might never have arisen. Never. It's a strange paradox that the most violent ends of stars give rise to the raw materials for new beginnings. As we drift deeper into this story, keep in mind the scale. These are not just curiosities. They are part of the great cycle of stellar life and death. They shape galaxies, they ripple space-time, and they remind us of the vast power of nature. And so, as we ease further into the night, imagine yourself watching a star collapse, watching its brilliance fade, and knowing that what remains is not an ending, but a transformation. That transformation is where we'll stay for a while, exploring every layer of what it means to be a neutron star. Because in their density, their violence, and their mystery, they may just hold answers to some of the most profound questions we can ask about the universe. When you picture the night sky, it's easy to think of stars as eternal. They shine with such steadiness that from one lifetime to the next, they seem unchanged. Yet every star has a story. And like any story, it has a beginning, a middle, and eventually an end. The most massive stars, the ones many times larger than our sun, live especially dramatic lives. Their births are violent, their youth is extravagant, and their deaths are among the most spectacular events in the universe. To understand where neutron stars come from, we need to follow the journey of one of these giants, from its bright beginnings to the moment it collapses in on itself. Stars are born from clouds of gas and dust, the raw material of the cosmos. Gravity gathers these clouds together, pulling atoms closer until they heat up and ignite nuclear fusion. Once fusion begins, a star is alive in the truest sense we can use that word for an object of plasma. Hydrogen atoms fuse to form helium, releasing light and heat that radiates across space. In a star like our sun, this process is balanced and stable, allowing it to shine for billions of years. But in a giant star, the kind we're interested in tonight, things happen faster and with more intensity. A massive star burns its fuel at a furious rate. Its light is brighter, its temperature hotter, and its lifetime shorter. Instead of billions of years, it may last only a few million. That sounds long to us, but on cosmic scales, it's brief, almost like a spark compared to a slow, glowing ember. The reason is simple. Gravity pulls more strongly on a massive star, and to resist that pull, the star must generate greater pressure from fusion. That means it consumes its hydrogen more quickly, racing through its supply like a bonfire that devours wood. As the hydrogen runs out, the star turns to new fuel. Helium becomes carbon becomes oxygen, and so on, building heavier and heavier elements in its core. Each stage happens more quickly than the last, as if the star is sprinting toward a finish line it cannot avoid. By the time iron begins to form, the star has reached a dead end. Iron cannot release energy through fusion. It costs more energy to fuse than it produces. For the star, this is the moment of crisis. Without new energy to push outward, gravity gains the upper hand. The balance that has held for millions of years breaks. The star's core begins to collapse inward, compressing under its own weight. Imagine a sphere the size of the Earth's orbit suddenly giving way, its mass rushing inward at a significant fraction of the speed of light. Temperatures soar to billions of degrees. The outer layers, unable to resist, fall inward as well, then rebound in a massive explosion. This is a supernova, one of the most powerful events in the cosmos, bright enough to outshine an entire galaxy for a brief time. Supernovae are not just fireworks. They are creative acts as well as destructive ones. The shockwave from the explosion forges new elements, scattering them into space. Gold, silver, uranium, and countless others are born in this chaos. Every heavy atom in your body, every trace of iron in your blood or calcium in your bones was forged in the death of a star. We are quite literally made of stellar remnants. That poetic truth is grounded in physics. But what of the core that triggered it all? That collapsed heart of the giant. Here, the story narrows to a scale almost impossible to imagine. The inward collapse squeezes protons and electrons together, creating neutrons. In fractions of a second, the core becomes a sphere of neutron-rich matter, only about a dozen miles across, yet still holding more mass than the Sun. The density is so extreme that normal language fails to capture it. Saying that a teaspoon of this matter weighs billions of tons is true, but even that metaphor is difficult to picture. Imagine taking all the mountains on Earth and compressing them into something that fits in your hand. That is the density of neutron star material. This collapsed core does not continue collapsing indefinitely because something resists. The neutrons themselves, governed by quantum mechanics, push back against further compression. This push is not like any ordinary force. It arises from the rules that particles follow, rules that prevent them from all occupying the same state. This resistance halts the collapse, at least temporarily. If the star's mass within a certain range, the core stabilizes as a neutron star. If it is greater, even this resistance is not enough, and the collapse continues until a black hole forms. For those that survive as neutron stars, the transformation is complete. The brilliant bloated giant is gone, and in its place is a tiny, dark, unimaginably dense sphere. It no longer shines like an ordinary star, but it is far from lifeless. It can spin, it can radiate beams of energy, it can quake and ripple with magnetic storms. It is the corpse of a star, yet in many ways it is more active than the star ever was. Consider the violence of that transition. A massive star steady in the sky for millions of years suddenly collapses and explodes in just seconds. In that brief moment, it releases more energy than our sun will in its entire lifetime. The core that remains is so dense that space-time itself bends sharply around it. Light passing nearby curves and time runs more slowly close to its surface. It is a place where the familiar rules of the world we know are stretched into strange shapes. You might imagine this collapse is rare, but in our galaxy alone, it has happened countless times. Astronomers estimate that hundreds of millions of neutron stars exist in the Milky Way. Most are invisible to us, silent and dark, but some reveal themselves through bursts of radiation or rhythmic pulses of radio waves. These are the pulses, the cosmic lighthouses, which we'll wander towards soon enough. For now, it is enough to know that every one of them is the grave of a giant star, a reminder that even the brightest lives come to an end. Yet calling it an end feels misleading. What remains is not nothing. It is something new, something strange, something that continues to affect its surroundings in profound ways. Neutron stars are like fossils of physics, preserving conditions that cannot be recreated in any laboratory. By studying them, we gain insights into the behavior of matter at densities far beyond anything on Earth. They show us how nature behaves when pushed to its absolute limits. If you look up at the night sky and see the soft glow of stars, it's hard to connect that beauty with the violence of collapse. And yet hidden among those points of light are the remnants of explosions long past. Somewhere in the constellation of Cassiopeia, there is the famous Crab Nebula, the expanding cloud of a supernova recorded by Chinese astronomers in the year 1054. At its center lies a neutron star spinning 30 times a second, still radiating after nearly 1,000 years. That remnant, small and dense, is the collapsed heart of a giant. This cycle of life and death, of birth, collapse and transformation, continues throughout the universe. Stars form, they burn, they die, and from their ashes come neutron stars, black holes, and the seeds for new generations. The collapse of giants is not just a curiosity of astrophysics, it is the mechanism by which the universe renews itself. Every heavy atom around you is proof of this. The story of neutron stars is not just out there in space. It is written in your bones, in your blood, in the world around you. And so as we move forward, remember that a neutron star is not merely a collapsed object. It is the testimony of a life once lived. A blazing star that shone, collapsed, and left behind something stranger and denser than we can truly imagine. These remnants are the bridge between the ordinary stars we see and the mysteries of space-time itself. They are both an ending and a beginning, a paradox made real. When you hear that a neutron star holds more mass than the sun inside something no larger than a city, it sounds like exaggeration, a kind of cosmic metaphor. But it is not a metaphor at all. It is a straightforward fact of physics, one of those truths so extreme it feels unreal. Imagine taking everything the sun contains, all of its hydrogen and helium, all of its burning layers, all of its mass that stretches nearly 1 million miles from side to side, and then pressing it down until the entire object fits comfortably inside the area of a large metropolitan skyline. That is the scale we are dealing with.